So, this is the lecture 6 and the first module, neural networks, the course on intelligent control. Today we will take up a new another architecture of learning system that is used widely in control system. This is called radial basis function network, and the network architecture is given here. You can see is that it has 3 layers. First layer is as usual the input layer. The second layer, which is hidden layer, is different from the computational unit in the hidden layer. They are different in structure compared to the multi-layered network that we discussed. These computational units are known as radial centers. It is radial center because if I look at C1 has the same this is P into 1 vector. So, same is x vector, which is P into 1, the input vector. And this centers they represent the clusters. The centers here, they represent the clusters in the input space, the C1, C2 and CH. They represent the clusters in the input space. So, CIs represent clusters in the input space. The output of each center is which is phi I. The output phi I is a function of the distance, Euclidean distance between Ci and x. So, you can say that now the computational unit has a different function than the multi-layer network. And then what you are seeing is that we compute this phi i's. The CI's are known as radial centers. They represent small clusters in the input space, and then the y, the output, is simply summation. The output is simply summation of phi I wi. Okay, I equal to 1 to h. So, this is the structure of a radial basis function network. There are certain advantages we will talk about. Let me say what we talked just now. So, radial basis function networks consist of 3 layers: input layer, hidden layer and output layer. Unlike in multi-layer network, you can have as many hidden layers you can have, but here you can have only one hidden layer, and the computational units in the hidden layer has a different function than that of multi-layer network. The hidden units provide a set of functions that constitute an arbitrary basis of input patterns. Hidden units are known as radial centers and represented by the vectors C1, C2, CH, and they have the same vector dimension as that of the input x. Transformation from input space to hidden unit space is nonlinear, whereas the transformation from the hidden unit space to output space is linear. That is what we talked about, that here the phi i's is a nonlinear transformation of x input. Actually, this is a function of the norm or the Euclidean distance between Ci and x, which we normally represent by the second norm. And also we talked about that, so this is nonlinear, phi I is a nonlinear function of xi, whereas y, the output, is a linear function of phi. So there is a difference, and dimension of each center for a p input network is p by 1, that I have already told. So this is our network that we discussed, and the radial basis functions in the hidden layer produces a significant non-zero response only when input falls within a small localized region of the input space. So to explain this, let me explain this. So we are talking about input space, all right. So these data, they belong to this input space. So the input space, instead of being represented by each and every data, the principle in radial basis function network is, say for example, the inputs are datas, say they are all distributed in the trunning set like this. So if this is the data, each point represent a data in this input space. So we can easily say, okay, let us select from this bulk of data 2 clusters here, another 2 cluster here, another 2 cluster here. This is a small data point, 1 cluster, another cluster. What is meaning of cluster? This is another point that represent the data around this. Similarly, this is another point which represent the data around this. So what happens? So when the input data is very near to this cluster, then the output of this cluster or output of this center is will be maximum, and the response of this radial center. So what? Let me first clarify what I am trying to tell you. What I am telling that we have a radial center, okay, and these radial centers are placed in the hidden unit, and these radial centers are the clusters in the input space. Input space means a space where all possible data in the input are located. Okay. That means we are trying to map, we are trying to construct a map from the input space to output space. Okay. So in the input space, all possible varieties of data are there. So in the radial centers, they represent this data. So in a sense, in an ideal case, input space may contain infinite number of many data, not infinite but many data. Okay. And to represent this data using finite data points, and these finite data points are known as clusters. Okay. So each cluster has its own receptive field, in the sense that each cluster represents certain data point, and for those data point, that cluster output, that radial center output will be maximum. So that is in the hidden layer. I place these clusters in this hidden layer. Okay. So for example, this cluster is this cluster. If I say, then the output of this cluster or radial center will be maximum for the data lying in its receptive field, and obviously the output of this for any other data in this away from this radial center will be minimal. Okay. So that is the idea. So radial basis function in a hidden layer produces a significant non-zero response only when the input falls within a small localized region of the input space. Okay. Each hidden unit has its own receptive field in the input space. which I just told you that the output will become maximum for a radial center when the data input data belongs to its receptive field. An input vector xi which lies in the receptive field for center Cj would activate Cj, and by proper choice of weights the target output is obtained. The output is given as y phi j wj. Phi j is phi x minus Cj norm. Actually this is a phi represents a function, what I said earlier. So, as already I have told, y output is a linear function of the outputs of the radial center, which is phi j, and phi j is a nonlinear function of x, which is a nonlinear function of distance between x and Cj. So, phi is some radial centers, and then what are these radial functions? There are certain popular radial functions. If we define z as a norm, Euclidean norm between x, the input data, and the center, j's center, we have say h centers we saw, and the j center and x, the distance is Euclidean distance. You can easily say that this is the Euclidean distance between x and Cj, and the types of radial functions that normally we use are Gaussian radial function, thin plate spline function. Gaussian is very popular, e to the power minus z square by 2 sigma square, where z is the Euclidean distance between the data and the radial center, and similarly the thin plate spline function z square log z, and phi z is z square plus r square to the power half, is a quadratic function. The third one, inverse quadratic, is just 1 upon z square plus r square to the power half, that is root square z square plus r square. So, normally the Gaussian function has been very popular in the while selecting radial center. What is the normal difference between a radial basis function network and multi-layer network? The difference is a radial basis function network has a single hidden layer, and multiple layer network has multiple hidden layer. So, MLN has multi-layer network, RBFN has single hidden layer. The basic neuron model as well as the function of the hidden layer is different from that of output layer. The output layer we have simply summation, where the hidden computation is as I said you, they are function of the Euclidean distance between input and the center, whereas the computational units in multi-layer networks are all similar. The hidden layer is non-linear, but the output layer is linear. Here all layers are non-linear, but not necessarily. Sometime in multi-layer network also we can make the output layer to be also linear. So, radial basis function network, activation function of the hidden unit computes the Euclidean distance between input vector and the center of that unit, and activation function of the hidden unit computes no, it's a little different here, is a function of Euclidean distance between the input vector and the center of that unit. Okay. So, the activation function is a function of Euclidean distance between input vector and the center of that unit in radial basis function network, whereas in a multi-layer network the activation function computes the inner product of the input vector and the weight of that unit. In a sense, it's all right, I can always say. So, the objective here, whatever is written, is just a comparison. What is happening is that the activation function is a function of Euclidean distance between input vector and the center, whereas this is an inner product. The activation function is a function of inner product. So, it is not function, activation function. The idea should be very clear to all of you that here the the function phi is a function of Cj, whereas this is the sigmoidal function here phi. If I say it is also phi, then in this case is f of x transpose w. Okay. The weight, connection weight associated with the input. So, such weight is absent in this case, radial basis function network. Radial basis function network establishes a local mapping, hence capable of first learning, and the multilinear network constructs a global approximation to input output mapping. Here the learning in the radial basis function network consists of two different categories of parameter. One is centers, radial centers, and the other is the weights, the connection weights in the output layer. Whereas in multi-layered network, the only parameters are the synaptic weights. So then what we have in a radial basis function network, the parameters are C1, C2 up to CH. These are all centers, and W1, W2, W up to Wn, these are weights. Okay. The weights are in the output layer and the centers are in the hidden layer. So the training of RBFN requires optimal selection of parameter vectors C and W, weight vector. So, we have to select in such a way that given x and y, given this set of data x and y, the yd minus y. So, yd is the desired output and y is the radial basis function output, square half over all patterns I equal to 1 to say m, okay, number of patterns. So, this cost function must be minimized. So, the objective is select C i's and w i's such that this particular function is minimized. So, this is the objective. The following techniques are used to update the weights and center of RBFN. There are many methods by which these centers and weights are all optimized. One is the very simple is pseudo inverse technique, which is an offline technique, gradient descent learning and hybrid learning. These are all online technique. Gradient descent is same as back propagation, what we talked about in multilayer network. What is a pseudo inverse technique? So, this is a least square solution. What we do here, let me tell you. So, what you have here, we have inputs, then we have hidden units, then we have output unit. Okay. So, given here x p, some x p, we compute what is y p, all right. So, what we do here in pseudo inverse technique, radial centers are fixed. So, how you fix the radial center? Because the radial center represent the clusters in the input data space. What I can do is that this is my input data space. So, I have a stack of data, input data. What I can do is that I can randomly sample this data, and each data I put I assign each data, each random sample from this data to Ci's. So, what I do, Ci is assign a random sample from input space. From the input space or input data, I select a random sample and assign to Ci, and like that I assign all the centers. Okay. The objective is that centers should be so selected they are almost like uniformly distributed in the data. That means, wherever there are more data points, from there more data should come, and where there are less data points, like for example in this zone there are more data points. Okay. In this point there are more data points. So, more number of points should come and become as this should be assigned as a radial center, and these are sparsely say these data points are very sparsely located in this zone, then very few points should come and be assigned as the radial center. That is the objective. Okay. So, that way we can fix the radial center. So, once the radial center is fixed, then the outputs are known, then these phi i's are fixed, because phi i's are based on whatever the centers are fixed. So, phi I is fixed given a specific data point. So, given a specific data point, what we have now? Now, these weights Wi, phi I, sorry, I have to write like this. I have to write like this, that this is phi is a vector, W also is a vector. So, I have to write phi, yeah, phi I Wi. This is right. Phi I Wi is same as phi transpose W. Okay. So, this phi I Wi is now Yp. So, for each xp I can collect this kind of equation, all right. So, I have how many unknowns? The W's are you can see here the number of parameters now to be estimated are this is actually not n, this is h, Wh. So, the number of weights are h, because centers are h. So, number of weights are h for single output radial basis function network. So, if you look at, so we have Wi's I equal to 1 to h. Okay. So, for each input pattern, for a given input pattern, we compute this, we find out this equation phi transpose W is Yp. So, like that, how many equations we have? P equal to 1 to capital M, where M is number of data pattern. All right. So, you have these many equations, and how many unknowns? Unknowns are h number of weights, these are unknowns. So, obviously, normally the data patterns are many, and h is usually h is less than, much less than m, h is much less than m. Okay. So, in a sense you have more number of equations, less unknown. So, we can easily find a least square fit. So, that is the objective here. So, this is a least square problem. Assume a fixed radial basis functions, Gaussian function. So, we assume that all the radial centers in the hidden units are Gaussian functions. The centers are chosen randomly, as I said. The standard deviation of the radial function is determined by an ad hoc choice. Learning steps are as follows. The width is fixed according to the spread of the center. So, your phi I is exponential function or like a Gaussian function e to the power minus h upon d square, and this is the norm x minus c, Euclidean distance between x and ci square. Okay. So, this is the distance square. So, how do we find h is the number of centers and d is the maximum distance between the chosen center. So, what is meaning of this maximum distance between chosen center? If we go back, let us say that we have two dimensional data x1 and x2. So, I have a data point one cluster here, another cluster here, okay, and all other clusters are like this. So, obviously, this cluster and this cluster, the distance between this is maximum. Okay. So, similarly, once you have fixed the radial centers, find out two centers that have maximum distance between them. All right. Once we do that, then that is d, that maximum distance is d. Okay. Then obviously, if you look at that, if I write this e to the power minus x minus c I, the Euclidean distance square by sigma square, if I write, then sigma will become d upon root 2 h, 2 sigma square. Normally, the function is like this, a z square by 2 sigma square. So, this is a normal form of a Gaussian function, and if I represent this function as this, which is written here, then obviously sigma is d upon root over 2 h, and d is the maximum distance between any two radial centers. So, we have already now we will formulate the problem. Problem is, let us say phi is phi 1, phi 2 up to phi h. It is a row vector, it has taken here, it is a row vector phi. So, these are the output of the radial centers. W is the weight vector, this is a column vector, and phi w is yd, yd is the desired output. So, we are now only talking about a single output RBFN. You can also talk about multi output, the same, the formulation will be same. So, required weight vector is computed as so what I am trying to do here is that we will find pseudo inverse technique how to solve a radial basis function network. So, for a pth pattern, phi p is a vector of phi 1 p, phi 2 p up to phi h p. So, these are the outputs of the radial centers, okay, and weight is W 1, W 2, W h, and corresponding output is Y d p. Similarly, we have n patterns. If I write this in terms of matrix, I can write a capital phi, which is phi 1 1, phi 2 1 up to phi h 1. So, these are the radial center output for first pattern. Second pattern phi 1 2, phi 2 2 and phi h 2, and so on. Mth pattern is phi 1 capital M, phi 2 capital M, and so on, phi h capital M. This is my phi, and correspondingly each one is multiplied with W. So, this, let me not put it here, this I put it here. So, this is my big phi, and if I multiply with this with W 1, W 2, WH, because they are fixed. Okay, they are fixed for a set of, the weights are fixed. What we are trying to do is that it is a offline training, a pseudo inverse technique. We will allow the patterns to pass through the network, compute the YD, store them for M patterns, and while doing all these things, weights are all fixed. And hence, what we are doing is we are keeping all those the regression vectors, which is phi 1 to phi 2, this phi vector, and we are equating with the output. Obviously, phi 1 1, phi 2 1 up to phi hn, if you multiplied with this weight vector, corresponding output is YD 1 pattern. Second one is YD 2, and the mth one is YD m. So, what we got, a matrix notation, this is phi, this is weight, and this is, I can say, capital Y. All right. So, now you can easily see, because output is a linear relationship, has a linear relationship with weight. So, we can always represent in terms of matrix format, and the solution, and you can easily see that Y is m by 1 vector, W is h by 1 vector, and this the phi is m by h vector. Okay. So, the solution will be that phi capital Phi into W is Y. So, this is we found out this is m by h, h by 1, and this is m by 1. So, obviously, since this is not a square matrix, we can't invert it. So, the solution is very easy to find out when phi is a square matrix and invertible. But when it is not a square matrix, what we can do? We use pseudo inverse technique. What is pseudo inverse? I multiply phi transpose phi W. So, phi transpose is H into M cross H. So, this is H cross H matrix, right. So, this is H cross H matrix, and W is H cross 1, and here we multiply here phi transpose Y. Okay. So, this is H M 1. So, this is again H cross 1. So, everything is satisfied. So, finally, the W is phi transpose phi inverse phi transpose Y, because this is now a square matrix. But this solution is possible only when, so the solution that we got the solution for W is now phi transpose phi inverse phi transpose Y. So, this is known as pseudo. See, the solution is possible. Solution is possible only when phi transpose phi inverse exists. Otherwise, also we can use singular value decomposition. Singular value decomposition method when this is singular. Okay, singular means its determinant is 0. Okay. So, this was a little mistake there. I corrected that. So, what you found out that required weight vector W is phi transpose phi inverse phi transpose YD, okay, and this is known as the pseudo inverse of phi. This is possible only when phi transpose phi is non-singular. If this is singular, singular value decomposition is used to solve W. That is the summary. So, this is an example. Example is that we take a function x nor function 0 0 1 0 1 0 1 0 0 1 1 1. This is a x nor function. We select two centers. So, centers can be selected randomly from the input space. So, in input space we have 4 data. So, we can select any one of them. Let us select 0 0 and 1 1 as the centers. So, C1 is 0 0 1 of the center, the other center is 1 1. So, phi 1 is exponential minus x minus C1 square, and phi 2 is e to the power x minus C2 Euclidean norm square. So, where x is x1 and x2. This is the output y is W1 phi 1 plus W2 phi 2 plus theta. If you look at here, theta is the bias we have. So, this is the architecture we selected. This is the architecture, radial basis function network architecture selected to learn the function x nor, all right, and we have taken two radial centers and one bias. The bias input is plus 1, the bias weight is theta, right. So, y is W1 phi 1 plus W2 phi 2 plus theta, and phi 1 phi 2 are computed according to this. We have 4 training patterns. So, if we compute for each pattern the phi 1, so the phi 1 for the first pattern is 1, is obvious because you can easily see here for the first pattern 0 0 and C1 is 0 0. Obviously, e to the power this Euclidean distance is 0. So, e to the power 0 is 1. So, that is what you are saying. So, W1 into phi 1 is 0 here, and phi 2 is e to the power minus 2 because the Euclidean distance is root 2 and square is 2, e to the power minus 2. So, W1, and we have taken here to let you know that we have only taken e to the power Euclidean distance square, that means sigma equal to 1 we have already selected. So, it is implies here 2 sigma square is 1, all right, in the Gaussian function. So, based on that, for each pattern, this is for 0 0, this is the next pattern 0 1, 1 0 and 1 1. Obviously, for 1 1 phi 2 is 1, all right. So, this is the 4 equations we have for 4 data pattern. If we form a matrix phi into W equal to YD, phi W is YD. If we put this, then YD is 1 0 0 1, that is the your this is YD is 1 0 0 1, and this is your phi W. So, W is W1 W2 theta, we have 2 weights and 1 bias. If you solve using pseudo inverse technique, where W is phi transpose phi inverse phi transpose. So, this is inverse phi transpose. So, this is this value 2.5, 2.5 minus 1.8, this is a column vector. So, this is the solution. So, to conclude that if we have already a data, some set of data, input output data, we have no restriction for online training, then pseudo inverse technique is good. So, if data set is already available and no demand on online training, then pseudo inverse technique is a good approach to find weight vector W. So, this is our weight vector. Now, we talked about pseudo inverse technique where we fix the radial center, but imagine the situation where the data is coming online and we have to do online training. Okay. Like for example, in control system. In control system, data, when we do a control system, data is coming online and we have to train our controller online. So, in that case, how the training should be done? So, gradient descent as usual. So, instantaneous gradient descent is a good method for it. So, this is a very again the same methodology, that once you are given instantaneous cost function E, Cij t plus 1 is Cij t minus eta 1 del E upon del Cij, and this can be easily updated. And similarly for weight also we can do the another gradient descent, okay, where is the instantaneous cost function Yd minus y. Okay, these are instantaneous values. These are all scalars, not vectors. So, of course, for just to give an example, I will be little faster here because we have already discussed lot about gradient descent derivation. So, our y is phi I wi, phi I is e to the power minus z I square upon 2 sigma square, where z I is x minus c I, Euclidean distance between x and c I. Sigma is the width of the center, differentiating E with respect to wi. Okay. So, you get this particular thing. Okay. So, obviously, the weight update is wi t plus 1 is wi t plus eta error yd minus y into phi I. This is the weight update for weights in radial basis function network. That is very simple because it is a linear network, whereas the weight update of center, imagine each center has p elements, because the x, the input is p dimensional vector. So, that is why if you look at the derivation del E upon del C I, so this is this particular thing. First you differentiate E with respect to y with respect to phi I, and phi I is a function of Cij, and Cij is not there in any other phi, any other radial, only ith radial center contains the element Cij. This is important, and hence this expression is right. So, we already know del E upon del y is this, del y upon del phi was wi, and to compute phi I by this, we differentiate phi I with respect to z I with respect to Cij. So, when you differentiate phi I with respect to z I, we get z I upon sigma square phi I negative, and similarly z I with respect to Cij, we get this expression, right. So, we have now this is here negative, this is also negative, this is also negative. So, overall the sign of this expression is negative. So, Cij t plus 1 is thus, this is our final expression for Gaussian centers. And this is for weights. So, this is a simple derivation, you can verify for yourself. So, using this gradient online training instantaneous gradient descent, we will now do a system identification of a source tank. We have already discussed what is a source tank. Source tank is is there to to minimize the effect due to sudden pressure or sudden pressure in the water reservoir. Normally in hydro power plant you have a water reservoir, suddenly the level increases. Okay. So, then from a water reservoir there is connection to the turbine and other things. So, if the sudden increase is there, then the flow increases. So, to maintain the same flow we place a source tank here. Okay. So, the flow goes up and tank height, the liquid level in the tank increases. So, if the source tank the volume is a nonlinear, has a nonlinear relationship with the level h, then the one of the model of such a source tank is this, which is a nonlinear model. St plus 1 is St plus T into this quantity, where Ht is the liquid level, Ut is the flow inside this source tank. So, what you are seeing here, let me do like this. This is our reservoir. So, this is the water reservoir, this is the source tank, and we are only concerned the model of this source tank, and this model of the source tank is if the flow, there is a certain flow rate into the tank, then how the level of the tank increases. Okay. For a nonlinear thing, this is for a discrete dynamic model of the source tank. Please see that T into minus 2 square root 2 GH upon square root 3 H plus 1 plus Ut upon 3 Ht plus 1 square root. Ut is the flow, water flow into the source tank, Ht is the liquid level, G is the gravitation acceleration due to gravity, T is the sampling time, and T is the sampling instant. So, data we have generated in the similar manner earlier we have done. Sampling time 0.01, 150 data has been generated using this data, that our input flow is according to this particular curve and corresponding Ht liquid level. So, this is your Ut and this is your liquid level, corresponding liquid level. So, we selected a radial basis function network. Obviously, it has two input, one target, two input is Ut and St, target is St plus 1, units in hidden layer are 30, number of input output data is 150, radial basis function is Gaussian, width of radial function sigma is 0.707, center learning rate eta 1 is 0.3, weight learning rate is 0.2, and this is the convergence. You can easily see within 200, less than 200 epoch, the convergence is achieved to achieve the RMS square root mean square error 0.007, below 0.007, and when we give a new input, that is the input flow follows this particular curve, then the liquid level, here the red curve, you can see that red curve and the green curve, these are all over the red curve there is the green curve, and red is desired, and the green is actual. Okay. So, you can easily see that the RVFN model that has been trained, which is took 200 epoch, could easily map or could easily learn the dynamic of the source tank. So, this is the third. So, we talked about two different learning, pseudo inverse and gradient descent. Now, we will talk about a new kind of learning that is normally employed for radial basis function network, which is called hybrid learning. What is hybrid learning? That center and weights are separated. Centers, since they represent the clusters in the input space, we can use unsupervised learning to learn the cluster centers, whereas the supervised learning for the weights. So, hybrid learning means unsupervised learning for centers and supervised learning for weights. In hybrid learning, the radial basis functions relocate their centers in a self-organized manner, while that is the unsupervised learning, while the weights are updated using supervised learning. When a pattern is presented to RVFN, either a new center is grown if the pattern is sufficiently novel, or the parameters in both layers are updated using gradient descent. The taste of novelty depends on two criteria: is the Euclidean distance between the input pattern, the nearest center, greater than threshold, is the mean square error at the output greater than a desired accuracy. A new center is allocated when both criteria are satisfied. Okay. But normally the best way is that the easiest way to do this center learning using classical clustering is that we fix the number of centers, okay, and assign them random in vectors from the input space. This is the first step. This is the step 1. In step 2, this is the step 2. What in step 2 we do? Once the centers are fixed, okay, uniformly sampled from the input space, then what we do? We present an input pattern, find the Euclidean distance between this input pattern and all these centers which are already fixed, and the numbers are also fixed, and then find the winner. Whichever is the winner, we update the weight of that winner. So, this is for the winner. And for all other centers, we do not do any change, the centers remain as it is. And we repeat this process for all the data set in the training set, from the all the data pattern from the training set. So, this is called k-means clustering. This is called k-means clustering. So, not only this radial centers can be used k-means clustering, there are other clustering techniques, we will not now focus on that. We will just give an idea how this is done. So, clustering, so unsupervised manner, and what about the weights? Weights can be used because weight and the output, they have a linear relationship. We can use any least mean square, we can use also gradient descent. Apart from gradient descent, we can also use the least mean square algorithm or recursive least square algorithm. Okay. There is also this is a recursive least square algorithm. I will not tell that in this class, maybe later. And same the search tank also can be modeled using this hybrid learning, where k-means clustering has been used with the learning rate 0.5, which is alpha, that is alpha is 0.5, and the gradient descent method has been used for weight update, where the eta is, this is eta, this is alpha, and root mean square error, the training is terminated when root mean square error was less than 0.007. So, you can easily see in the beginning, when we reshuffled this the centers were uniformly distributed. So, these are the centers, these squares, circles are the centers, and this is my input data in the, this is my u, this is my h, this is my h and this is my u. Okay. So, what you are seeing is that in the before unsupervised learning, the centers are all uniformly, randomly distributed, and this is the data, and as we presented data to the centers using k-means clustering, you will see that most of these centers were aligned with the data, input data, and very few left unaligned. Okay. So, this is the final comparison of the result. What we are seeing is that when we train a search tank, do the system identification of a search tank using backpropagation network, that is multi-layered network, radial basis function network using gradient descent, radial basis function network hybrid learning, then the number of iterations that are required, you see that backpropagation takes long time and the radial basis function network takes less time, and RMS error is same because we have fixed the RMS error, but the training is terminated over the same RMS error. Okay. So, obviously, the same RMS error for the new data, that means generalization for all the three networks are same. Okay. So, final conclusion is that today we discussed RVFN network, and we talked about three types of learning. First one is pseudo inverse, which is a offline training. Second is the normal gradient descent, and third one is hybrid, which is a combination of unsupervised plus supervised. Okay. So, thank you very much.